Hello everyone, we are in section 1.5 and in this section we're going to talk about tangent lines and rates of change. This will be the last section of chapter 1 for us. Now coming to this section, we already talked about limit and continuity in the prior sections. So just want to show you something interesting here. This is an interesting function. I'm not sure if you've seen this or not, but if you have, then that's fine. If you haven't, you're gonna like this, I think. So, and this is a function that has many names. Actually, it's Thomae's function, the German mathematician Johannes Thomae. It also is known as Riemann function, and some call it a popcorn function because the what you're about to see, it looks like kernels of corn popping on the graph. And some call it the raindrop function, and it's also known as the stars over Babylon. Fancy, interesting, catchy names, right? So anyhow, but what's interesting about the function is this function, which is defined as 1 over q and 0, it's a piecewise function actually. Okay, so for when x is rational function and p and q are co-primes, in other words, the greatest common divisor of the two numbers is just 1. So for example, if you look at numbers 17 and 18, well, 17 is prime, right? So that would be 117, right? Two numbers that multiply to 17. A prime number is only divisible by itself and 1. And 18, you can write it as product or factors of 18, I should say, are 1, 2, 3, 6, 9, 18. Well, the only two common factors to 17 and 18 is 1, which makes 17 and 18 coprime. Okay. Now, anyhow, the first portion, the first piece of this function is going to work for rational numbers, and the function is going to be 0 if it is irrational. Okay. And so here's what's interesting about this function. This function turns out to be discontinuous if x is rational, and it actually becomes continuous if x is irrational. Okay. Now, here's what I've done for you in this graph. I use Mathematica to produce this function for you. Okay, and this function is graphed over the interval from 0 to 1. Now, if you look at the function, you're going to see it's a very interesting, amazing function, isn't it? So just want to show you this one because, again, most likely most of you coming from earlier classes have never seen functions like these. So just want to point that out. Now, what are we doing in this section actually? Tangent lines and rates of change. So let's actually briefly, I'm going to review slope of a line for you. Something, so let's just have fun with it. Okay, let's go back to your elementary algebra. Relax, this is something you already know, but we're going to modify it in calculus a little bit. And if you look at the slope of a line, when we talked about the slope of a line, we define the slope of a line to be the change in y over change in x, correct? So for instance, let's say I have 2 points here. I have point P and point Q, and suppose I'm just going to draw a curve through that for now. And here are 2 points, and I'm actually going to connect these 2 points together. So here's point P, that's point Q. Okay, and here's my line. The line L is called a secant line. Okay, a secant line is essentially a line that connects 2 points on the graph of a function. Okay, so here's my function. All right, and that's all that is. Now, I can find the slope of this line, couldn't I? And here's how we did it. Again, no mystery, you already know this. We look at the change in x, there's a change in y, call that delta y, call this delta x. So we're going to use Greek delta here. This is the second delta you're familiar with, and delta represents a change in the quantity it represents. The other delta we saw was this delta in epsilon delta definition. So those are the two deltas. So And we define the slope of a line to be the change in y over change in x, right? So that's all that is. So pretty simple. Now, if we have 2 points, therefore we can find the slope very easily. Now, what if I have only 1 point, not 2 points, and we want to find the slope of a line? Now, that's something we haven't done, and it's like, well, how can that even be possible, right? Because you need to have 2 points. So let's say I have this curve again, and we're going to make this point, let's say my secant line, I'm just going to make it go like this. So here's a point here, and there's a point there. Notice I'm making the points PQ closer to each other now. Okay, and I want to know what the slope of a line is now. Okay, and eventually what we like to do is this. Let's say I have this curve and I have a single point P, and I'm going to draw the line here tangent to the curve. And notice a tangent line can only touch the curve at 1 point, which it does in my case. So the question is now, what is the slope of this line? It is a line, so it's got to have a slope. The trouble is now that I only have 1 point, I don't have that second point Q. So how are we going to do this? And that is the objective, I should say, the objective of this section. Okay. So let's take a look at this. So the way we're going to go about this is the following. So I'm going to just draw this thing out, and then we formally define the slope of a tangent to the graph at 1 point. So here's how it's going to make sense for us. As I mentioned, we're going to make this point. So I'm just going to do now a large blow up of this. So suppose now this is point A, and here's a graph of the function f over restricted domain. Okay, it's just portion of it. And there you go. This is the tangent line. Okay, so it is a tangent line. And that means it's going to cross, or not cross, but it's going to touch the function at only 1 point. So this is line L. This is how we're going to go about doing this, because we really need to have 2 points. There is no way around that. Okay, so what we do in order to find the slope of this line is this. Rather than going over here, where I'm just too far away from the function, and create a second point, and then try to find, let's say right in here, some distance later, h units later, and then try to find the slope of a line between these 2 points. Why don't we make this point as close as possible, the second point, that is the a plus h. Why don't we bring this point in, go in that direction, make it closer and closer to a. Now as this point gets closer and closer to a, then we can actually look at the slope of the tangent line at that point. Okay, so in fact, when we make this closer and closer to a, we're gonna look at h very close to a, within like maybe delta unit of a. That's how close we want it to be. Remember, epsilon, deltas, these are small numbers. So I'm gonna make this h a very small amount, and here's how we're gonna define the slope then of the tangent line. Okay, so this is going to be the slope of tangent. Let's call it tangent line to the graph of f and we're going to make it at a point at call it a, and f at a, at a single point. Notice we've never done that. So the slope of a line is defined as m for the slope of the tangent line, tan, which is the same as the slope at point A. We're going to look at the limit as h goes to 0. Remember, we're going to make h approach a and get very close to a. Of this would be the change in y, f at a plus h minus f at a. That's the change in y on the function. over h. And note here what we're doing is actually this. We're making a secant line. Okay, let me draw this part over here. So this is how the a and h work. This is the a, and we're drawing a secant line. Let's make my secant line, actually, let me draw a different curve for you. Let me go this way, and let me see the slope of it. No, then you get confused. Let me stay with what I had. There you go. And we're going to make this to be a. Okay. Now, if I draw a secant line right in here, this is my secant line, that's the function. This distance is h. So I'm going to look at the change in y. Remember, the coordinates of this point are going to be f at a plus h, and the coordinates of this point is f at a, right, and a. The other point, the y value is f at a plus h, and let me just write the full coordinates for you. This point is at a plus h, that's the x value, and f at a plus h. So in other words, we're not using the points that are on the tangent line. Okay, so we're going to actually use the secant line, the line that includes points that are on the function. And then we're going to look at this is delta y and this is delta x. Now imagine as h gets closer to 0, as h goes to 0, delta x, the change in x, approaches 0 also, doesn't it? Okay, and when that happens, the 2 points reduce down to almost a single point, in that h is an infinitesimal unit away from a, very, very close to a. So that's what this is. So the numerator of this fraction that I have in the limit form is the change in y, and the denominator is the change in x. Remember, as you go from a to a plus h, the change is h units. Okay, and that's what that is. And there you have it. So this is how we're going to define the slope of a tangent line. Okay, and if I actually now graph this one, let me use a different color marker. So this is what we're actually doing. We're looking at this line. This is the secant line. And we're going to use the secant line to actually find the slope of that tangent line. As h gets closer to a, the secant line itself turns into a tangent line. Okay, and there we have it. So let's actually take a look at an example right off the bat here. Okay, so let me change my pen and grab my black pen. This should do. Okay, so in this example, let's take a look at the following. Let's say we want to find the slope of the tangent line, the slope of a tangent line. Let's make it to the, say, graph of y equal x squared plus 2. It's a simple parabolic function. And we want to find the slope when a, let's make a to be, let's go a negative 1. Okay, when a is negative 1. Okay. And we also want to find the equation of the tangent once we find the slope. Find the equation of tangent. In order to do that one, we need to find the slope of the line. Okay, so here's how we're going to do this. First, I'm going to graph this function. Okay, when we graph this function, again, this is a simple parabola, right? X squared is the basic parabola. X squared plus 2 is a parabola that is shifted up 2 units. So let's say this is what my parabola looks like. So this is x squared plus 2. Okay, now at -1, this is -1. I'm this far away from 0, -1 away from 0, and let me now use my different color marker here. So I'm going to draw the tangent line at that point. And this is what the tangent line looks like, right? It's really attached at that point. Just want to make sure you can see the line well. Now at -1, well, if you plug in -1 into the value of the function, the point is -1 comma 3, isn't it? That's this point. We want to find the slope and the equation of that line. That's what we would like to do. So how do we find the slope? Well, the slope of the line at point A is going to be the limit as h approaches 0 of, again, we have f at a plus h. Let me do that one maybe in here. Well, f at a plus h, because this is x squared plus 2, we're going to replace x with a plus h. So that means a plus h squared plus 2, right? That's by definition of a function. So this one, we're going to, now this is for general a, right? Since we have a, let me just say at a equals -1, therefore this becomes f at -1 plus h, doesn't it? That's what it becomes. So this becomes a -1 plus h squared plus 2. I replace a with -1. Okay. So I'm going to write the limit. If we keep a in our limit, then we find the general slope for any tangent line for any given a. We'll do that later. It's just the first example. We want to make it a little easier. So that's what f at a plus h is. Now f at a, remember a is -1. f at a, that's x squared. X is -1 now, plus 2. And then divided by h. Okay, and notice in the limit, by the way, the denominator is 0, so you have division by 0. All of the limits that are in this form for the tangent line have denominator 0. So these limits, they seem to be undefined and they need to be worked out. So we can't jump to a conclusion that the limit cannot be found. Now, if I expand the binomial in the numerator, -1 plus h squared, you square the -1. Plus twice first by second, well, that's 2 times -1 by h is -2h plus h squared plus 2. Negative. Inside the bracket, the second bracket, -1 squared is 1. 1 plus 2 is 3. So I'm going to go -3. Okay, and that's divided by h. I'm going to shrink that line a little bit. Okay, now if I work the details of this limit, let's simplify the numerator. The limit as h goes to 0 of, it's going to be -2h plus h squared, right? 1, 2 makes 3, and -3 is 0 divided by h. And note this, when you directly substitute, you're going to get 0 over 0. Looks familiar? Remember the indeterminate form of limits. All of the limits for tangent lines will be 0 over 0. Okay, so let's take a look at this one. How are we going to work this one? I'm going to factor, we got to work around this division by 0, right? That's what the culprit is, the h in the denominator. So I can actually factor the h in the numerator and swap out the two terms. Instead of -2h plus h squared, I'm thinking h squared minus 2h. And then, see here, we can divide the h's out. Now directly substitute for h. When h is 0, we get 0 minus 2 or -2. So notice, 0 over 0 doesn't equal to 0, and it doesn't equal to 1, anything like that. So please be sure that you work these limits. All of these limits will be in determinate form. So there, we found the slope. This is the slope of a tangent line at that point. Okay, slope's going to be -2. Now, the equation of the tangent line, we're going to go y minus y1, point slope form of a line. And let's see, at point, remember we are at point -1, 3. So here's my x1, here's my y1. So it's going to be y minus 3 equal the slope we found to be -2, x minus -1. And that is y minus 3 equals -2x. Double negative in parentheses makes +1 times -2 distributes makes -2. And from this we get -2x. Add 3 to both sides and we have the equation now of the tangent line, and that is our equation. See how that works? So it's pretty simple but yet powerful idea here. Okay, so again, it is possible to find the slope of a line at a single point, point by introducing the limits. And we're just going to make the limit as h approaches 0. Okay, that displacement away from A, from the point of tangency, is going to be very minute and very small. Okay, now we're going to take a look at let's think of this as some kind of a physical application that we're going to look at later on. We're going to look at 2 definitions to wrap this up. Okay, so our first definition, this one, we're going to call this the average rate of change. Okay, so the average rate of change of a function f over a closed interval a and a plus h. And that is given by f at a plus h minus f at a divided by h. And that's what's called the average rate of change of a function over that interval. And again, the idea is this. If I graph it, here's x. Let's say the function does this. Here's point A, and actually I'm doing a plus h, right? Let's go like that. And I'm exaggerating this. H is not this far away from A, but this is A plus h. Again, we're looking at distance h units away from A. This is f at A, and the value of function is f at a plus h. So now notice that this function actually varies, right? As you move from point A to point A plus h on the x-axis. The function changes, but it doesn't change in a linear fashion. It changes in a non-linear fashion. Within that tiny interval, in fact, it can actually fluctuate like this, like I had it before, over that little interval a plus h, between a and a plus h. There you go. So it's not a uniform change. That's why we called it the average rate of change. And to find the average rate of change, you look at the change in y as you go from a to a plus h. Again, this is your delta y, and you divide it by the distance h. Okay, and that gives you the average rate of change of the function. Notice you do not take the limit. Okay, this is because we don't want it at a point. We actually want from at t equals 0 and then at t equal 1, maybe a second later. Okay, so this is the average rate of change over a closed interval. Now we do have, if you're interested in the rate of change at a point, which we call instantaneous rate of change, we do the limit now. So let's call that, in fact, let's go instantaneous rate of change of a function. Now, this would be a function f at x equals a. Okay, so this instantaneous rate of change means change as it reads, the change in an instant of time. Limit as h goes to 0 of f at a plus h minus f at a divided by h. So all the instantaneous rate of changes is the average rate of change, is the limit of the average rate of change. There you go. That's what this is. This is the limit of the average rate of change. Without the limit, it's just the average rate of change. Once you take the limit in an instant, that's what that is. Now, of course, these limits don't always exist, so this is provided the limit exists. Okay, and that's what this is about. Okay, now we'll be looking at some examples in a moment next. Okay, so actually before we look at one example, I want to just emphasize this. This is a graph from your book, and I just want to emphasize some of the things we went through, just so there is a better maybe sketch for you to grasp this. In this figure, this is from your book, remember the line that connects 2 points on the graph of the function is called the secant line, right? So in this example, another example, but in this sketch, this is your secant line. Okay, that's what that secant line is. Now, what we're doing here is notice this point Q is getting closer and closer to the actual point P. So there you go. It's going in this direction. That's what the direction of arrow says. So we're getting closer and closer to Q. As you do, the secant line is closer also, and eventually the secant line turns into the tangent line T. That's what that is. So this is something we talked about. I thought this is a good illustration of it. Now, the other idea was the limit of the quotient. By the way, that expression that we saw, this expression f at a plus h minus f at a over h, what we looked at, we call this a difference quotient, and we will look at difference quotients extensively in chapter 2 when we talk about derivatives of a function. Okay, difference quotient. So again, the idea here is that you're looking at the change in y over change in x as you go from one point to the next point right in here. And this would be your secant line, right? That is your secant line this way. Okay. And as this point moves closer and closer and closer to the lower point, the higher point, upper point, closer to lower point, when it gets this close, let me erase these. When it gets, let's say, this far away from it, and look at when I connect them, I'm almost touching the curve now. So that's just the illustration of what's going on in here. This h is a tiny distance, by the way. It's exaggerated, magnified many times here. So we're talking about maybe realistically, look at my pen. There you go. You see the dot here? That's where h is. That's how far away from a we want to be, which on the graph it puts me right about here. Now imagine drawing a line through that. So we're going to get very close to the tangent line there. Okay, so here's our difference quotient. Let's take a look at some exercises. There's not that many in this section. There's about 30 or so. But let's take a look at exercise. I don't know, something simple for now. Let's begin with exercise number 8, and then we'll look at another one. In exercise number 8 here, part A, we want to find the slope of a secant line through points AFA and h units later. So this is a general slope we want to find for the general point. M secant is going to be the difference quotient, f at a plus h minus f at a, and the denominator is actually a plus h minus a, but then these cross out, so that's why we only have h in the denominator. Okay, so which is truly the change in y over change in x. So the slope of the secant line is therefore, now f at a plus h, we're going to plug in a plus h in for x, right? So that's going to be 2 times, it's going to be a fraction. So it's going to be 2 times a plus h plus 3. That's just f at a plus h minus f at a. Well, f at a is 2 times a plus 3 divided by h. Distribute, we can see 2a and 2a, those add to 0, so I have 2h plus 3 minus 3 add to 0, so it's 2h over h, which reduces down to 2. Okay, so it looks like the slope of a secant at any point, remember we kept a general in part a, so the slope of that line is 2, right? Now that's interesting. How can that be? When you have a linear function, let me draw this line. Suppose this is 2x plus 3. Well, and here's a point. If I draw a tangent to this line, how is that tangent line to the line is going to look like? Well, the tangent line, there you go, it's the line itself, and that line has a slope 2, so your slope is always 2. At this point, draw a tangent, there it is. At this point, draw a tangent, there it is. So you're always drawing the line itself. Okay, and there, so that makes sense. So in other words, for linear function, the slope is exactly the same as the slope of a line. The slope of a tangent at any point is the same as the slope of a tangent, the same as the slope of a line. Okay, now in part B, it says, okay, use the result of part A, which slope is always 2, doesn't matter now. What they want you to do now is we want to find the slope of a tangent at the point AFA. AFA for number 8 is this point. In other words, at point 1, 5. So imagine this is 1, 5. There you go. They say, what's the slope at that point? Well, it doesn't matter. The slope of the tangent is going to be the limit of the slope of the secant line that we just found as h goes to 0. And the limit as h goes to 0, remember the slope of a secant was 2, and the limit of a constant is constant. So slope of a tangent, and this is at x equals 1. Okay, or a, they use a, didn't they? There you go, at a equal 1. In part C, find an equation of a tangent at point AFA. So, and remember, A is 1, FA is 5 here. So in part C, we're looking at 0.15. The slope of a tangent, I'm going to be 2. It's always 2 for this one. So using a point slope form of a line, y minus y1, m x minus x1, we can actually find this. Okay. And let's take a look at this one. So how is this going to work out? We're going to plug them in. So I get y minus y1 is 5 equals slopes 2 x minus 1. So we have y minus 5 is equal to 2x minus 2, or y equals 2x, add 5 to both sides. That's the equation of the tangent line. Now, interesting. Check this equation and check out the problem itself. You see that? Oops, sorry. That's exactly the same, isn't it? We just found the slope of a tangent to be exactly the line itself. This happens for linear functions. Okay. Now, let's do something that this doesn't happen for. So something like, for instance, number 14. So I'm doing number 14 now. In number 14, f of x is equal to 1 over x plus 1. And we want to do the same thing. So first we want to find the general form of a slope of the secant line. The secant line is at any point on the graph, okay? So that's what that is. In part A, slope of secant line is simply f at a plus h minus f at a divided by h. Okay. Now f at a plus h, we're going to plug in a plus h in x. So that's going to be 1 over, remember we're going to replace x with a plus h. So it's a plus h plus 1 minus f at a, change x with a, you get 1 over a plus 1 divided by h. And that's our difference quotient. Now, we have a complex fraction here, so I'm going to multiply the top and the bottom by the LCD. The LCD is a plus 1 times a plus h plus 1. I'm going to multiply the top, which is 1 over a plus h plus 1, 1 over a plus 1, and the bottom, which is simply h times LCD. This is the easiest way to get rid of complex fractions. Okay, now when I distribute the LCD, I'm looking at these two. When I multiply those two factors by the first fraction, distribute, so the a plus h plus 1 right in here and a plus h plus 1 here will disappear. So this is going to be a plus 1 because a plus h plus 1 disappears, minus the second distribution of the factor in front of parentheses times fraction 1 over a plus 1. This time a plus 1 and this a plus 1 disappear, right? Those cancel, cross out. And now I can write this as negative of a plus h plus 1 divided by all of that stuff in the denominator. And then if I distribute the sign in the numerator, I get rid of those 1 and negative 1 add to 0, so I have negative of h over the denominator, which has an h in it, a plus 1, a plus h plus 1. Multiply h times 1 because you're about to cross it out. So it looks like the slope of the tangent at every point on the graph of this thing is going to be an oblique hyperbola. Okay, it's going to be negative 1 over a plus 1, a plus h plus 1. That's at every point. Okay, that's the slope of a secant line. Now, in part B, the slope of the tangent line is going to be, and we want that at what point? We want it at point in number 14, at point 1 and 1/2, right? A is 1. Okay. There we go, at point 1 and 1/2. This is A. So the slope of the tangent is going to be the limit as h goes to 0 of the slope of the secant, which is your difference quotient. It's easier for me to write it this way. And remember, we have the slope of a secant, right? We just found it in part A. So if I take the limit now, the limit as h goes to 0 of negative 1 over a plus 1, a plus h plus 1. So we're going to do two things. We're going to plug in 0 for h, and we're going to plug in a 1 for a. But let me find this limit. And this is now the slope of a tangent line at any point. The one in part A gives you a slope of a tangent and the slope of a secant at any point, and this is the slope of a tangent at any point. So I'm just going to plug in A was 1, so that's 1 plus 1 times 1 plus 0 plus 1. Looks like negative 1. This is 2 and 2, 4, negative 1/4. Okay, and that's going to be the slope of a tangent line for exercise number 14. Okay, and the equation of the tangent, y minus y1, mx minus x1. So it's going to be y minus y1 is 1/2, and the slope we found it to be negative 1/4. X minus x1 is is 1. So that's going to be y equals negative 1/4 x. Negative 1/4 times negative 1 is 1/4, and I'm adding is 1/4 and add 1/2 to both sides. That's going to be negative 1/4 x plus 3/4. That's going to be the slope of a tangent at that point. Now again, I mentioned the graph of this thing is some kind of an oblique hyperbola, but there you go. This is what this graph is going to look like. The graph of let's see, number 14, 1 over x plus 1. So this is going to be, let's say, x plus 1. At x negative 1 we have a vertical asymptote because the function cannot be negative 1. You have division by 0, right? If it's x plus 1, yeah. And then you can see, you can plot points and figure this out. This is what I meant by oblique hyperbola, that is shifted from the origin, away from the origin. And this part, of course, is not touching, it's just, there you go, it goes asymptotically close to line x equals negative 1. So what we found at point 1 and 1/2, 1 and 1/2 is this point right in here. That's 1, and this is point 1 and 1/2. Okay, and we found the slope of the line to be this right in here. There you go. It's almost a 0. The slope's 0, right? Negative 1/4 plus 3/4. Y-intercept at 3/4, and the slope's negative 1/4. Very flat. All right. So there we have this problem worked out. Now let's take a look at another example here. In our next example, let's take a look at, we did number 14. Okay, let's take a look at maybe one down here. For this next segment, we do a couple. In this one, the question reads, find instantaneous rate of change of the given function when x is a. So we want instantaneous means change in an instant of time. Okay, so it's almost immediate, the change at that point. So let's take a look at something like number 18, for example. F of x is root x, a is 4. Okay, so I'm going to look at number 18 actually. Let me change my pen. Okay, in number 18, f of x is root x, and the point at which we want to find the instantaneous rate of change of the function is a4. Now for this one, just to graph it, it's not difficult to graph this one. So you have your basic square root function. This is 4 and here is x. Alright, so let's take a look at how this is going to work out. Okay, so we want to find the instantaneous rate of change of the function at a4. Okay, so let's do this. The instantaneous rate of change is going to be the limit as h goes to 0 of f at a plus h minus f at a over h. True? So we're going to go limit as h goes to 0 of f at a plus h is going to be root a. Well, a is 4, right? So let me just actually plug in a 4 here, makes it easier. 4 plus h minus f at a means square root of 4 divided by h. Okay, now let me move this a little more to the left so I have more room. So this is limit as h goes to 0 of square root of 4 plus h. That's going to remain. Square root of 4 is 2. It's going to be that over h. Again, if you plug in a 0 right now, you're going to get 0 over 0 indeterminate form. So the way you work the limits with the square roots in this course, most of the ones we're doing anyway, you multiply by conjugate. So I'm going to do square root of 4 plus h plus 2, and then square root of 4 plus h plus 2. Okay, and that's going to be the limit as h goes to 0 of. Now in the numerator, we know that we have difference of two squares, right? A minus b times a plus b is going to be what? A squared minus b squared, right? We know that. So we're going to get 4 plus h square root of that. There's your a squared minus b squared over all of the denominator, 4 plus h plus 2. So that's going to be the limit as h goes to 0. Notice how you have to put this expression every time you write the limit. Without it, it would be incorrect. So that's going to be 4 plus h minus 4 over h times square root of 4 plus h plus 2, right? And the h's cross out, and the limit is going to be, and plug in 0 for h. So we're going to cross out this h. So all I have is a factor of 1 in the numerator. So it's going to be 1 over square root of 4 plus 2. Square root of 4 is 2. 2 plus 2 is, the square root doesn't actually go on 2 here, just to make sure. Let me tidy up this thing. The way I did it looks as if the square root goes all the way to 2. It doesn't. Okay. So that's going to give you root 4 plus 2, which is 4. So the instantaneous rate of change at that moment of time, the curve is changing at the rate of 1/4 unit in y per unit change in x. Okay, so there you go. That is the answer to number 18. Let's take a look at a different problem now. So let's take a look at actually exercise number 24 here in your book. Okay, let's do that. Number 24. Let's bring it over to my note. Okay, so in exercise number 24, the question goes: during the construction of a high-rise building, a worker accidentally dropped his portable electric screwdriver from a height of 400 feet. After t seconds, the screwdriver had fallen a distance of s as a function of time t, 16t squared. How long did it take the screwdriver to reach the ground? In part B, what was the average? Well, we'll get to those other parts. So in part A, how long did it take the screwdriver to reach the ground? Okay, so since we were given the disposition function, that is 16t squared, right? That's your disposition, is 16t squared. And by the time it hits the ground, it must have traveled 400 feet, right? So we're going to set it equal to 400 feet in order to find t. Therefore, t squared is 400 divided by 16, and that's going to be, what, 25? True? So t is going to be plus or minus 5. Of course, because t is time, t must be positive. So that means 5 seconds later, the screwdriver is going to hit the ground. Now, in part B, what was the average velocity of the screwdriver during the time it was falling? Now, the average velocity, remember, velocity is disposition per unit of time, right? So let me write that. Velocity is the change in distance over change in time. True? So for us, that means we need to do this. We need to look at because it took it 5 seconds. So we're going to look at the value of the function at 5. That's our disposition function at 5 minus the disposition function at t0, which amounts to 400, right? Divided by change in time 5 minus 0. That's the fancy way of doing it. I'll show you the common sense way of doing it in a moment. Over 5, and this is going to give us 80 feet per second, right? That's the velocity. Now here's what I was saying, because we're talking about the average velocity, right? Not instantaneous. This is average velocity. So we simply look at the displacement change. 400 feet happened in 5 seconds, right? There you go, 80 feet per second. But again, because that's just an average, instantaneous is going to be different. This is the easy way of doing it, but we want to make it a little fancier, so we use the formula earlier. Now in part C, what was the velocity of the screwdriver at the time it hit the ground? Okay, so at the time it hits the ground, let me put that, it hits the ground 5 seconds later, right? 5 seconds later. So we want to know in that instant of time, what is the velocity, right? So we're looking at instantaneous velocity now. That would be the impact velocity. The limit as h goes to 0, right? H goes to 0 of the average velocity, f at 5 plus h minus f at 5 over 5 plus h minus 5. Okay, so this is going to be the limit as h approaches 0 of, now we have 16t squared, that was our function, so that's 16 times 5 plus h squared, minus f at 5, that means 16t, but t was 5, so that's 16 times 5 squared over h. And even now, if you plug in the numbers, you're going to get 0 over 0. So we need to work this one further. So the limit is, as h goes to 0 of, in the numerator, we're going to factor 16, right? There's a 16 here, 16 here. So we're going to factor the 16s out. And that's going to be 5 squared, 25, plus 2 times 5 is 10 h, twice first by second, plus h squared, minus, remember we factored the 16 out, so we only have 25. And that last term is just that, over h. The 25s cross out, and this is going to be the limit as h goes to 0 of. Now, there's 16, and I'm going to factor the h. It's going to be 10 plus h over h. Now the h is crossed out, and that's how you get rid of 0 over 0. Okay, so let's see, at this point, let's see, f at 5, okay, everything looks good here. And plug in h0, and this is going to be 16 times 10, or 160 feet per second. Okay, and that's all this is. Okay, so we're done with this section, and with that we are also done with the chapter. So please take a look and try to do some of these homework problems from section 1.5. All right, and that concludes this lecture.